Welcome to the channel for you. Fat. This article is about the type of nutrient in food. For fat in humans and animals, see adipose tissue. For other uses, see fat disambiguation. A space-filling model of an unsaturated triglyceride. In nutrition, biology, and chemistry, fat usually means any ester of fatty acids, or a mixture of such compounds, most commonly those that occur in living beings or in food. The term often refers specifically to triglycerides, triple esters of glycerol, that are the main components of vegetable oils and of fatty tissue in animals, or, even more narrowly, to triglycerides that are solid or semi-solid at room temperature, thus excluding oils. The term may also be used more broadly as a synonym of lipid, any substance of biological relevance, composed of carbon, hydrogen, or oxygen, that is insoluble in water but soluble in nonpolar solvents. In this sense, besides the triglycerides, the term would include several other types of compounds like mono and diglycerides, phospholipids such as lecithin, sterols such as cholesterol, waxes such as beeswax 1, and free fatty acids, which are usually present in human diet in smaller amounts. Fats are one of the three main macronutrient groups in human diet, along with carbohydrates and proteins, and the main components of common food products like milk, butter, tallow, lard, bacon, and cooking oils. They are a major and dense source of food energy for many animals and play important structural and metabolic functions in most living beings, including energy storage, waterproofing, and thermal insulation. The human body can produce the fat that it needs from other food ingredients, except for a few essential fatty acids that must be included in the diet. Dietary fats are also the carriers of some flavor and aroma ingredients and vitamins that are not water-soluble chemical structure. The most important elements in the chemical makeup of fats are the fatty acids. The molecule of a fatty acid consists of a carboxyl group O smiley face C- connected to an unbranched alkyl group CHX NH. Namely, a chain of carbon atoms, joined by single, double, or, more rarely, triple bonds, with all remaining free bonds filled by hydrogen atoms 5. The most common type of fat, in human diet and most living beings, is a triglyceride, an ester of the triple alcohol glycerol HCHOH, 3H and 3 fatty acids. The molecule of a triglyceride can be described as resulting from a condensation reaction, specifically, esterification, between each of glycerol's O groups and the HO part of the carboxyl group O smiley face C- of each fatty acid, forming an ester bridge O smiley face C- with elimination of a water molecule H2O. Other less common types of fats include diglycerides and monoglycerides, where the esterification is limited to 2 or just 1 of glycerol's O groups. Other alcohols, such as cetyl alcohol, predominant in spermaceta, may replace glycerol. In the phospholipids, one of the fatty acids is replaced by phosphoric acid or a monoester thereof. Conformation. The shape of fat and fatty acid molecules is usually not well defined. Any two parts of a molecule that are connected by just one single bond are free to rotate about that bond. Thus a fatty acid molecule with N-simple bonds can be deformed in N1 independent ways, counting also rotation of the terminal methyl group. Such rotation cannot happen across a double bond, except by breaking and then reforming it with one of the halves of the molecule rotated by 180 degrees, which requires crossing a significant energy barrier. Thus a fat or fatty acid molecule with double bonds, excluding at the very end of the chain, can have multiple cis-trans isomers with significantly different chemical and biological properties. Each double bond reduces the number of conformational degrees of freedom by 1. Each triple bond forces the 4 nearest carbons to lie in a straight line, removing 2 degrees of freedom. It follows that depictions of saturated fatty acids with no double bonds like stearic, having a straight zigzag shape, and those with one cis bond like oleic being bent in an elbow shape are somewhat misleading. While the latter are a little less flexible, both can be twisted to assume similar straight or elbow shapes. In fact, outside of some specific contexts like crystals or bilayer membranes, both are more likely to be found in randomly contorted configurations than in either of those two shapes. Stearic acid is a saturated fatty acid with only single bonds, found in animal fats, and is the intended product in full hydrogenation. Oleic acid has a double bond, thus being unsaturated, with cis geometry about midway in the chain. It makes up 55 to 80% of olive oil. Alidic acid is its trans isomer. It may be present in partially hydrogenated vegetable oils, and also occurs in the fat of the durian fruit, about 2%, and in milk fat, less than 0.1%. Vaccinic acid is another trans acid that differs from alidic only in the position of the double bond. It also occurs in milk fat, about 1 to 2%. Nomenclature: common fat names. Fats are usually named after their source, like olive oil, cod liver oil, shea butter, tail fat, or have traditional names of their own, like butter, lard, ghee, and margarine. Some of these names refer to products that contain substantial amounts of other components besides fats proper. Chemical fatty acid names. In chemistry and biochemistry, dozens of saturated fatty acids and of hundreds of unsaturated ones have traditional scientific technical names usually inspired by their source fats: butyric, caprylic, stearic, oleic, palmitic, and nirvanic, but sometimes their discoverer, Mead, Osbond. A triglyceride would then be named as an ester of those acids, such as glycerol 1,2-dialeate-3-palmitate. 6. IUPAC. In the general chemical nomenclature developed by the International Union of Pure and Applied Chemistry (IUPAC), the recommended name of a fatty acid, derived from the name of the corresponding hydrocarbon, completely describes its structure, by specifying the number of carbons and the number and position of the double bonds. Thus, for example, oleic acid would be called 9-COCTADEC9-enoic acid, meaning that it has an 18-carbon chain octadeck, with a carboxyl at one end, OIC, and a double-bounded carbon 9 counting from the carboxyl, 9N, and that the configuration of the single bonds adjacent to that double bond is cis, 9Z. The IUPAC nomenclature can also handle branched chains and derivatives where hydrogen atoms are replaced by other chemical groups. A triglyceride would then be named according to general ester rules as, for example, propane 1,2,3-tril 1,2-bis 9Z OCTADEC 9-enoate 3-hexadecanoate. Fatty acid code: a notation specific for fatty acids with unbranched chain, that is as precise as the IUPAC1 but easier to parse, is a code of the form ND. Cis CCC. Trans TTT, where N is the number of carbons, including the carboxyl 1D is the number of double bonds, CCC is a list of the positions of the cis double bonds, and TTT is a list of the positions of the trans bounds. Either list in the label is omitted if there are no bounds of that type. Thus, for example, the codes for stearic, oleic, alidic, and vaccinic acids would be 18-0, 18-1 cis 9, 18-1 trans 9, and 18-1 trans 11, respectively. The code for alpha-oleostearic acid, which is 9E, 11E, 13Z OCTADECA9, 11, 13-trinoic acid, in the IUPAC nomenclature, has the code 18-3 trans 9, 11 cis 13. Classification. Main article. Fatty acid by chain length. Fats can be classified according to the lengths of the carbon chains of their constituent fatty acids. Most chemical properties, such as melting point and acidity, vary gradually with this parameter, so there is no sharp division. Chemically, formic acid 1 carbon and acetic acid 2 carbons could be viewed as the shortest fatty acids, then triformin would be the simplest triglyceride. However, the terms fatty acid and fat are usually reserved for compounds with substantially longer chains. Citation needed. A division commonly made in biochemistry and nutrition is citation needed. Short-chain fatty acid SCFA with less than 6 carbons e.g., butyric acid. Medium-chain fatty acid MCFA with 6 to 12 carbons e.g. capric acid. Long-chain fatty acids LCFA with 13 to 21 carbons e.g. petroselenic acid. Very long-chain fatty acids VLCFA, with 22 or more carbons e.g. Cirrhotic acid with 26, a triglyceride molecule may have fatty acid elements of different lengths, and a fat product will often be a mix of various triglycerides. Most fats found in food, whether vegetable or animal, are made up of medium to long-chain fatty acids, usually of equal or nearly equal length. Saturated and unsaturated fats for human nutrition. An important classification of fats is based on the number and position of double bonds in the constituent fatty acids. Saturated fat has a predominance of saturated fatty acids, without any double bonds, while unsaturated fat has predominantly unsaturated acids with double bonds. The names refer to the fact that each double bond means two fewer hydrogen atoms in the chemical formula. Thus, a saturated fatty acid, having no double bonds, has the maximum number of hydrogen atoms for a given number of carbon atoms. That is, it is saturated with hydrogen atoms. 7-8. Unsaturated fatty acids are further classified into monounsaturated MUFAs with a single double bond, and polyunsaturated PUFAs with two or more. 7-8. Natural fats usually contain several different saturated and unsaturated acids, even on the same molecule. For example, in most vegetable oils, the saturated palmitic C16-0 and stearic C18-0 acid residues are usually attached to positions 1 and 3 SN1 and SN3 of the glycerol hub, whereas the middle position SN2 is usually occupied by an unsaturated one, such as oleic C18-1, omega-9, or linoleic C18-2, omega-6. 9. Stearic acid. SVG stearic acid saturated, C18-0 palmitoleic acid structure. PNG palmitoleic acid mono unsaturated, C16-1 cis9, omega-7 oleic acid flat. SVG oleic acid mono unsaturated, C18-1 cis9, omega-9 alpha-linolenic acid. SVG alpha-linolenic acid polyunsaturated, C18-3 cis9, 12, 15, omega-3 gamma-linolenic acid. SVG gamma-linolenic acid polyunsaturated, C18-3 cis6, 9, 12, omega-6. While it is the nutritional aspects of polyunsaturated fatty acids that are generally of greatest interest, these materials also have non-food applications. They include the drying oils, such as linseed, flaxseed, tongue, poppy seed, perilla, and walnut oil, which polymerize on exposure to oxygen to form solid films, and are used to make paints and varnishes. Saturated fats generally have a higher melting point than unsaturated ones with the same molecular weight, and thus are more likely to be solid at room temperature. For example, the animal fats tallow and lard are high in saturated fatty acid content and are solids. Olive and linseed oils on the other hand are unsaturated and liquid. Unsaturated fats are prone to oxidation by air, which causes them to become rancid and inedible. The double bonds in unsaturated fats can be converted into single bonds by reaction with hydrogen effected by a catalyst. This process, called hydrogenation, is used to turn vegetable oils into solid or semi-solid vegetable fats like margarine, which can substitute for tallow and butter and, unlike unsaturated fats, can be stored indefinitely without becoming rancid. However, partial hydrogenation also creates some unwanted trans acids from cis acids. Citation needed. In cellular metabolism, unsaturated fat molecules yield slightly less energy, i.e., fewer calories than an equivalent amount of saturated fat. The heats of combustion of saturated, mono, D, and tri-unsaturated 18-carbon fatty acid esters have been measured as 2,859, 2,828, 2,794, and 2,750 kilocalories per mole, respectively, or, on a weight basis, 10.75, 10.71, 10.66, and 10.58 kilocalories per gram, a decrease of about 0.6% for each additional double bond. 10. The greater the degree of unsaturation in a fatty acid, i.e., the more double bonds in the fatty acid, the more vulnerable it is to lipid peroxidation, rancidity. Antioxidants can protect unsaturated fat from lipid peroxidation. Cis and trans fats. Another important classification of unsaturated fatty acids considers the cis-trans isomerism, the spatial arrangement of the CC single bonds adjacent to the double bonds. Most unsaturated fatty acids that occur in nature have those bonds in the cis same side configuration. Partial hydrogenation of cis fats can turn some of their fatty acids into trans opposite sides variety. Oleic acid is the trans isomer of oleic acid, one of the most common fatty acids in human diet. The single change of configuration in one double bond causes them to have different chemical and physical properties. Oleic acid has a much higher melting point than oleic acid, 45 degrees Celsius instead of 13.4 degrees Celsius. This difference is commonly attributed to the supposed ability of the trans molecules to pack more tightly, forming a solid that is more difficult to break apart. 11. Omega number. Another classification considers the position of the double bonds relative to the end of the chain opposite to the carboxyl group. The position is denoted by omega-K, or N-K, meaning that there is a double bond between carbons K and K plus 1 counted from 1 at that end. For example, alpha-linolenic acid is a omega-3, or N-3, acid, meaning that there is a double bond between the third and fourth carbons, counted from that end. That is, its structural formula ends with CH equals CHCH2CH3, 12. Examples of saturated fatty acids. Main article, list of saturated fatty acids. Some common examples of fatty acids. Butyric acid with 4 carbon atoms contained in butter, lauric acid with 12 carbon atoms contained in coconut oil, palm kernel oil, and breast milk, myristic acid with 14 carbon atoms contained in cow's milk and dairy products, palmitic acid with 16 carbon atoms contained in palm oil and meat, stearic acid with 18 carbon atoms also contained in meat and cocoa butter. Examples of unsaturated fatty acids. Main article, list of unsaturated fatty acids. Myristolic acid C14-1, omega-5, cis-9 tetrade cenoic acid. Sapienic acid C16-1, omega-10, cis-6 hexadecanoic acid. Palmitolic acid C16-1, omega-7, cis-9 hexadecanoic acid. Oleic acid C18-1, omega-9, cis-9 octadecanoic acid. Petroselenic acid C18-1, omega-12, cis-OCTADEC6-enoic acid. Cis-vaccinic acid, C18-1, omega-7, cis-11 octadecanoic acid. Vaccinic acid C18-1, omega-7, trans-11 octadecanoic acid. Oleic acid 18-1, omega-9, trans-9 octadecanoic acid. Trans-oleic acid, linoleic acid. Linolenic acid. Paulinic acid C20-1, omega-7, cis-13 icosanoic acid. Gadolinic acid C20-1, omega-11, cis-9 icosanoic acid. Gondoic acid 20-1, omega-9, cis-11 icosanoic acid. Erucic acid C22-1, omega-9, cis-15 tetracosanoic acid. Brassidic acid C22-1, omega-9, trans-15 tetracosanoic acid. Nervonic acid C24-1, omega-9, cis-15 tetracosanoic acid. Arachidonic acid,